Hello guys, this is the heat transfer fastest revision video and this is meant for revision purpose. So let's just start because this is the fastest video. Please like, share and subscribe whatever you want to do with the video. Let's start. So first we know that the heat rate is for the conduction is Ka dt by dx. Okay, why minus? Because from this, if we are talking about the slab, so from a higher temperature T1 it goes to a lower temperature T2, and that's why the final minus initial value would be less. That's why we put the negative sign. Okay, now this is for a slab. We can say if it would be a straight line if the alpha, because the k would depend on k naught plus 1 plus alpha t sometimes. Okay, like this. So if this alpha is 0, that means our k is constant. That means this is alpha is equal to 0. If this is up like this, that means alpha is positive. When this is down, so up means positive, alpha down means negative. Okay, this is a very important thing. Now the resistance in the conduction, this is conduction, resistance in the conduction is L by Ka, and that for this conduction, and that for convection is 1 upon H. Units of K is very important. Units of K, how to find it? This is watt per meter square into meter upon Kelvin. So it is watt per meter Kelvin. So next, Newton's law of cooling. Newton's law of cooling, this states that the same convection term, so H A delta T, okay, where delta T here is T minus T environment, which I will write T infinity, okay, and here the resistance I will tell 1 upon H. Okay, now let's look at the pipe. Okay, let's say we take a cylindrical pipe like this, and here what will happen is that this pipe has some thickness. Okay, assume some thickness is also there, because obviously the pipe is not like this, it has some thickness. Every pipe has something. So there is an internal surface area, curved surface area of cylinder is 2 pi r h or L. R is radius, so this is the L. So that let's see that there is an internal area AI and there is an outer curved surface area A out, okay, AO, corresponding to DI and DO. Okay, so what we find out, the overall heat transfer coefficient, because inside there could be a convection, when outside is also there convection, so convection, and inside also convection, and in between this thickness there is conduction. So the net, this is a very long question sometimes asked. So the overall heat transfer coefficient, U is overall heat transfer coefficient, that would be basis on, if it is basis on the outer area, then it will be U into A. This is nothing but 1 upon HI AI, inner area, inner coefficient, plus the conduction. Now in the conduction, if it is a wall, if let's say cube, if it is a cubical tube, because first let me write about cubical tube, then it would be delta X, the thickness, upon Ka, and the outer convection and inner convection, outer convection, the conduction in the thickness. Here it is a wall. If it is not a wall, don't worry, and if it is not a wall, we just need to write the ln term, ln of Ro by Ri, outer by inner. Why? Because we want this ln term to be positive. Okay, that is a way to remember it. Outer by inner, ln, just put ln, and underneath that the same thing, Ka. Okay, now if and in fact the Ka, so area, always remember it is 2 pi r L. Okay, don't write it pi r square, never. It's curved surface area, because it is transferring like this, not like this. Okay, next thing is let's say in some questions there would be like, if Q is given, so like K naught 1 plus alpha T and dt upon dx, and some area is also there, area in a function of x. So remember, you need to integrate this t function with d. Okay, don't just take it out like that. Integration of a and x over there, and here integration here. Next there is let me say, like if some q value is there, okay, so a t upon t, and let's say ln, this is in case of RORI, let's write that. This is in case of cylinder, so 2 pi L K. Okay, this is in the case of cylinder, and let's say this is some heat, okay, Q naught, let's say, And in a different case, in sometimes the question is asked that if Q is reduced by 25%, then calculate something R or T. Okay, if Q is reduced. So in that case, if Q is reduced by 25%, that means the final Q is remaining 75% of the initial Q. And this way, equating this, you can finally get some value that would be missing in that question. So if it is reduced by 25%, it means the final value is 75% of the initial Q. This way, put this, equate this, and then do this. Okay. Now let me show you something that in a cylinder, the R mean, okay, the mean radius is not R, but it is calculated through log mean. How the radius is log mean in the sphere, it is geometric mean. Okay, it is, we have seen it is log mean, but in sphere, let's see, in sphere the formula is, let's say Q is A d1 minus d2. Okay, let's remove the A. Okay, like in cylinder it was log R rho by Ri by 2 pi L K. Same, do just this, because in sphere we have area 4 pi r square. Okay, or let's derive it. Okay, in case you ever forget this, just derive this. A 4 pi r square dt upon dr. Move that here, 4 pi k upon q, and let me write it delta t directly. Okay, integration, this is already integrated, this would be 1 upon r, so that means 1 upon r initial, r interior inner by rho. This would come over here, and delta t, this q will go over here, so q delta t and into 4 pi k. If I take this like this, if this goes down here like this, 1 upon ri minus 1 upon rho, so you can actually even get this in few seconds. And from above we take this down 4 pi k. So this is how you can do this. Okay, 4 pi k. Finally this pair is delta t upon 1 minus r I 1 upon ro. If you ever wonder what would be ri and what would be ro, just remember ri is small, so this term is more, that means it has to be positive. So positive, it will be positive when this term is more, and this 4 pi k for sphere. So what we see, this is r is of geometric mean, because why, you will feel that this is r o minus ri by ro ri. This cancel out with this dr. This is dr actually, so it will cancel out, and this ro ri will remain. And remember, this is geometric mean of this r. Okay, in case the question is asked like that. Now let's move to questions with heat generation. So heat generation, just one simple thing you need to remember. This is something that, the only thing in heat generation that you need to remember, r 1 upon r to the power n d by dr. Okay, bracket 1 upon, only thing that you need to remember is this equation k. Okay, k could be inside into d. Let me show you. So let me not write it outside. R to the power n. Okay, r to the power n outside, r to the power n inside. Okay, this way. Then we have d. Here we can write k. Sometimes k is not a function of t, so it can come out. So d kt upon d r. Okay, so d by dr, this is also d by dr double, but inside between these two it is sandwiched. Okay, so r raised to power n, and outer it is divided also. This whole thing plus q dot is, so this whole thing plus q dot is heat generation per unit volume. Okay, per unit volume. Remember this, heat generated on source or sink, it can also be heat sink that would take up heat. So this whole thing, and I will tell you what it will be. This whole thing would be the change in the temperature, alpha dt upon dt. Okay, what, not alpha, it should be heat. So it is rho cp dt upon dv, but this is the change in time. If it is steady state, we can take it to be 0 if it is steady state. So steady state heat generation. In case of slab, or we can say Cartesian, so in case of that, n is 0. In case it is slab or some rectangular stuff or something, okay, cubical, n is 1. So first we see slab, likewise we took it for conduction, slab, then we take cylinder, and then we take sphere. Okay, just remember this equation. Okay, no need to worry about anything else, because let's say this is the equation, okay, for steady state, and let's say for cylinder I need to find out. Just make this 1, okay, r1 d by dr of k into r1 d by d of r into is equal to minus of q. So k, let me take it out, k here, and r goes there, integrate. So r dt upon dr is integration will prove r square by 2 plus c1, again divide this, so c1 by r, okay, again integrate. So finally we get, just in few minutes we can get, but you need to remember that basic equation, then you can find for everything. R square by 4 plus c1, r, this will be ln r, because this is integration, plus c2. C we find out easily, put the conditions, okay, the c1 would vanish in most of the cases. In some, if that case is given, apply that boundary conditions, and finally you get the equation. So remember just that one thing. Okay, next is the insulation, critical insulation. So in critical insulation, let's first see this, that this is the heat rejected, and this is the radius of the thickness. So how much insulation thickness is to be applied, this is the radius. As we increase the insulation, the heat will finally increase till a point, and then it will come down. So this point, this is when the maximum heat rejection, this is critical insulation, Ci, RCI, okay. And RCI is simple. See, RCI also has some very basic thing, K by H. One way to remember is that if you see if we know that L by Ka is a resistance and 1 by H is a resistance. 1 by HA is a resistance, and L by Ka is the resistance. So if A is common, we can see L by K is like 1 upon H, so L is K by H. In that way, similar fashion, R is equal to critical insulation is K by H. This is a way to learn this, okay. Next we have is okay, heat, that is also done. So for solid cylinder, there are 3 cases, like here T1, okay, if by chance, so this will be straight, let me make it straight, this is wall, and this is a wall straight, this is the hollow sphere above one, and the below one is, so no, below one should be hollow, above one because it is filled, so temperature gradient would be faster, and this would be the filled sphere. Sorry, above one, first is wall or slab, second cylinder, then finally sphere. And for solid cylinder, let's talk about that. For solid cylinder, it is T0 minus Tw, okay, this would be equal to R square by R square. Remember, it is proportional to R square. Solid cylinder. In plain wall, the heat conduction, that is in this way, if T1 is greater than T2 and there is a heat source, so heat source will increase the temperature like this. If T1 is greater than T2, if T2 is greater, then it will be the opposite like this. If both are same, it will be like this, middle point maximum, okay. And in case you want to learn that also for heat generation and something, then it is T0 by T0 minus Tw wall, this is x square by L square. Similar to like the solid cylinder and the solid wall is kind of same, just L, x and L are there, okay. And this is the ratio, T0 minus T. Sometimes we need to find this T at a particular x. Now there is, for cylinder, you can also remember just this thing if you really want to remember it directly. Q by K minus would be there, that has gone there, so T minus Tw minus Q by K into R square by 4 minus R square by 4. Remember that we had that R square by 4 term, okay. If you remember, you can go back to the video previous, and we can see this is for the cylinder, something this kind of thing came there. Now let's talk about fins. So fin is fine. Okay, fin is fine. This is a way to learn this, that E. So what happens in the fin? The profile is exponential, t minus t infinity upon ts minus t infinity. Difference between the, okay, so fin is like this. If I draw it, let's say I have a cylindrical fin. So this is t infinity everywhere. This is a t surface, and this is at any point t. So this by this, the difference between this and this. Okay, so difference between this divided by this is an exponential of minus mx. Let's see what is m and this thing. But fin is fine. Okay, remember that right away, that is exponential. So remember, this is like this at any part. Okay, because you don't need to mug this up. That's why I'm taking this in a little slow manner, because I don't want you to mug this up. Here heat is coming, then at this part, okay, because we are focusing on here, some heat will be lost like this from the surroundings. Okay, and then the rest will go here. This is just the fin. So conduction before this, let's say this is delta x, so at x, and this is conduction at x plus delta x or dx, and this is at the this is convection. So conduction, convection, conduction. Okay, same thing. So there is a difference, the conduction coming in and out, the difference in that is because of this convection. So let me write it very quickly. So Ka dt by dx at x plus dx minus this difference in conduction is because of this Ha delta t. Okay, now let A be there. So this difference, so this by this, and this is A can we write that like this, perimeter into delta x. Let's say if it is like this, this is a fin cross sectional area like this. We know the perimeter is like this whole thing. Okay, this is the perimeter. Okay, this perimeter into this is the curved surface area, the outer part. Curved surface area means the outer part. So this is perimeter into delta x. So we can write it hp delta x and delta t, and here if we put Ka common, so this is a difference between these two means delta of this. So delta of this divided by delta of this, so Ka common, delta of dt by dx divided by delta of x is equal to hp delta t. Now put this over here. So hp by Ka is something. Okay, I'm telling this because some people just mug up the right final formula, but no need to do that. Okay, so it will be now delta of dt by dx is del square t by del x square, and this will become, now we write hp by Ka as some quantity I will tell you, and this is t minus t infinity, that delta t. So let's write m is equal to this, we need m square. M square is hp by Ka. HP, okay, horsepower by Ka. Kakka Anna, I don't know. HP by Ka, you need to learn this way. Okay, so this is m square. There's a reason behind this m square, because finally we need the e to raised to power minus mx. Okay, so m is under root hp by Ka. Finally solving this, we get that equation that I told you. Okay, that exponential thing, and finally the q of fin is q of fin if the conduction and the convection both in the fin, the q is same, and that is write everything hp Ka. Okay, everything under root of hp Ka. This is the final equation. I'm not deriving it because it's a revision purpose, but I still derived that because some people just mug up blindly that. Okay, no need to do that. Into ts is this, okay, where the whole thing is there, some element. This is the fin, this is the element surface, the surface, and this is the infinity is the environment. So ts minus t environment into tan h ml. M we already know. Tan h comes because e to the power minus ml or mx. So in that way, e to the power minus something can be written as in terms of sine and cos. If you know that. If you don't know that, we know that e to the power iota theta is cos theta plus iota sine theta. Same ways, if it is e to the power only theta, then it would be cos h theta, okay, plus iota sine h theta, okay, this way, because iota is not there. So we can actually iota is almost like 1 upon h, almost like, it's not the thing, but it's like 1 upon h. So h would come here if iota and h, like this case, okay, 1 upon h if we take h. So this is something that the hyperbolic, I'm not explaining it, but it is kind of a similar fashion, like e theta, we do e theta plus e minus theta by 2, and something we write out because this is plus, so this will be cos, okay, cos hyperbolic because this iota is not there, okay. Iota, if iota was there, then it will be hyperbolic, it is cos theta. So you can just revise that in maths, I will tell you that over there, but the main thing is that tan h ml comes from there. And finally the efficiency eta is the q with fin. We have this fin at q, the actual thing, but what would happen if this fin was at temperature ts? If this surface temperature ts is all over this fin, what will happen? That will be the maximum rate, because slowly gradually this ts would decrease, but if it is all in ts, then that will be the maximum rate, heat rate, okay. So this fin upon fin by ts, and this comes out finally tan h ml by ml, okay. And eta is always less than 1. If it goes till infinity, you just don't need to apply some brain or something, just use the calculator, put a tan h m into some very long value, tan h into some very long value. So when you will put this a very large value, let's say 9999 in the calculator, it will come approximately to 1. So eta is 1 upon ml. If ml this is, or especially ml is goes till infinity, if L goes to infinity, n is eta is equal to 1 upon ml. Now effectiveness is, should we put the fin or not? Okay, so Q with fin and Q without fin. Obviously without fin we will have less heat transfer, with fin better way to, like, better heat transfer. So Q fin would be more. This is always greater than 1. Should we put the fin or should we not put the fin? This is greater than 1 while eta is always less than 1. Remember that. And this is given by PK. There is a movie also called PK. You can search the web later. PK, and by HA. PK. Remember here, PK I ho. Okay. That's a way to remember. So PK HA. Ha. PK by ha. Tan H ml. Tan H ml is, remember, this is everywhere. Okay. In also here in efficiency, this is effectiveness, in efficiency also, in the rate also, in the Q also, Q calculation. So this was like this for the lumped heat capacitance method. Remember one thing, very important thing, that tau, the time constant, is HA by M CP, rho CP or MCP. How? Because if we see, HA is Q upon delta T, MCP is Q upon delta T by dt by dt, delta T by delta T, capital T by small t. So Q cancel, delta T also cancel, and finally we have some, if this goes up, so 1 upon delta T. So time constant is HA upon MCP for lumped heat capacitance. Lumped heat capacitance method is applicable when Biot number is less than 0.1, or you can remember this by 10%, less than 10%. what does that means? What is Biot number? Biot number is HL by K. Okay, similar to like Nusselt number, but here remember solid is involved, so solid and plus fluid, while in Nusselt there is only fluid plus fluid, but this is solid plus fluid. Okay, and let's say this is a sphere and lumped heat capacitance is to be applied. That means K is very large. Okay, so that what happens that there is no gradient. If K is very large, so dt by dx would be very less, and therefore it's uniform temperature. The temperature is uniform everywhere. In fact, the outer temperature is different, and cooling upwards, mostly it's used for cooling like this. The final equation I'm writing, ln T is the final temperature that it will reach. So T by T my infinity is the environment, Ti is the initial temperature. This is equal to, now this will be minus because this term, this difference is more. This is more. Ti initially it is hot. This difference is more. It will cool down, so this difference will reduce. So this fraction, this ln will come negative. So here also on the right hand side negative, minus Ha by rho v Cp, okay, into T. So rho v, this is like m, so this is minus tau into T. Okay, tau unit is 1 upon time, so into time this is ln is dimensionless, unitless, so this will come unitless too. Okay, and instead of m, write rho v. So v and a, this is interesting, v and a, what we do, we get the characteristic length. Okay, characteristic length for so v by a, this characteristic length for cylinder, for sphere, let's say for sphere is pi by 6 dp cube upon pi by 4 dp square dp. So sorry, this is volume, right? So finally when you will do this, you will get 4 by 3. That's the characteristic length, and area is 4 pi r square. The overall surface area of the sphere, 4 pi r square, not pi by 4 dp square, 4 by r square. So r by 3 is for sphere, and for that cylinder it is r by 2. So again same thing, and 1 by r means L for solid cuboid kind of thing. So 1 2 3, the cylinder, sphere, and some cuboid, let's say cuboid or cube. Okay, cuboid will have a different thing, L into B. You can always do V by A. Okay, you understood that. Next thing, okay, one or most important thing, ln of that same term. Okay, this would be equal to, we know it is tau into T. What we can also write it as the Biot. Okay, I have to tell you the Biot on Fourier also. Basically it's minus Biot into Fourier, where Biot is HL by K, Fourier is Fourier number. Here is alpha T, because we need this T, alpha T by L square. So L this way would cancel, and alpha T by L square, and this is HL by K, alpha T by L square. This should be less than 10% or 0.1. Okay, next let me tell you about this case. If some side is insulated, what will happen, and the heat is generated, what will happen, this insulated will not let the heat pass, so heat will accumulate here, and the temperature will be hottest here, and also dt upon dx or something would be 0 at this surface, and the temperature would be like this, hottest over here if heat is generated. If heat is taken, then it will be lowest. Okay, and next one more thing is the hydrodynamic boundary layer by thermal boundary layer is almost equal to Prandtl to the power Prandtl number 1 by 3. Prandtl number we know, this is mu means rho upon viscosity upon density upon alpha. Alpha is heat diffusivity, thermal diffusivity. And also we know for flat plate, in case this comes, U by U infinity is equal to, this is the profile, 3 by 2, right, 1 by 2 minus this is y to the power 1, y1 so 3, y3 so 1. Okay, and 1 by 2 is always there. U by u infinity, infinity is the final, like this is the layer, so u infinity by u, and different y's for flat plate profile. H bar mean coefficient, heat transfer coefficient is 1 upon L, or on length basis then it will be 1 upon L local. Okay, local heat transfer coefficient from 0 to L. This is the mean average. So it comes mostly in cases it comes 2 of H in most cases. This depends on the flow pattern and where it is from. And Nusselt mean also comes 2 into N Nusselt. Nusselt is also H L by K. And let me write me some correlations that you need to remember. So first is Dittus-Volter equation correlation for turbulent. Remember turbulent. Okay, RE greater than, okay, 10,000, 10k. Please give me some 10k subscribers, please. Someday I will reach this much. Okay, so Renault 10k, and Prandtl should be always greater than 0.7. At least 0.7 should be greater than 0.7. So Dittus-Volter is the most famous. And for turbulent, okay, remember turbulent, this is Nusselt at any position x. Okay, you know that 0.023, 0.023, 0.0. So this is like, draw a cartoon first. This is the eyes, the nose, the eyes. Okay, and give him 23. My age is currently not just remember that your age is 23 currently, if your age is that. So that way you can 0.023, you can remember that way. Okay, I'm just trying to give you some help so that you can remember. Okay, into Renault to the power 0.8, because these are difficult to remember sometimes. So 0.8, okay, and Prandtl to the power 1 upon 3, not 1 upon 3, it is 0.3. It is 0.3 if it is cooling, so less if it is cooling, and 0.4 if it is heating. Okay, with the same thing, let's say 1 upon 3 we take, there is the same thing, see the tat correlation, the same thing is there, just mu upon, and also L by D ratio is something, L by D, so length upon diameter ratio should be greater than equal to 10. This is also, remember this just in case something like this asked. So mu upon mu, multiply by mu upon mu s to the power 0.14. This is a caesar tat. Mu upon mu s is also there. Okay, next thing, for a flat plate, Nusselt will be 0. For local Nusselt, it will be for flat plate. Okay, flat plate Nusselt, local Nusselt 0.332. Okay, Renault into 0.5. Okay, that was 0.8, but this is 0.5. Okay, Prandtl same. Prandtl is almost same, and we also know Prandtl raised to power 1 upon 3. This is delta H by delta T. Remember that, sometimes it could be useful. So hydrodynamic boundary layer by thermal boundary layer. This is for flat plate. Okay, and if you want the average, that means 2 into Nusselt number of x, so 0.664 into this same thing. Remember this 0.5, that was 0.8 there. Okay, this is flat plate. Let me write the for laminar also, in case it is asked. Laminar is again Nusselt. Okay, how to remember this? 1 point, you take first 1 point. Okay, it's almost 1 times. We know Nusselt is mean is Nusselt of this. So in laminar it is close, this is value is close to 2, and the closest thing to 2 is 1.86. Okay, this is how I remember this, because 1.86 is a very different thing to remember, but close to 2 into, now take here at the side mu s by mu w, like see that tat, and here what we need to take is the Renault and the Prandtl. Now put the power that Prandtl has, 1 upon 3 over there, and here L by D. Okay, this is for laminar. Somewhere remember it. Okay, try to like bookmark this part so that you can watch it later also, in case you forget. And for heat exchanger, there is one thing to remember, that is there is a range. So the range is delta T H by delta T C. Okay, H by C. This is the range, and there is an approach. Approach is delta T C by delta C max. Okay, so if we multiply range and approach, so it will be delta H by delta max. Delta X max means the hottest temperature minus the coldest temperature. Counter current, co-current, you know it, but still I'm telling you, this is co-current. Hottest in, coldest in at one terminal, and towards the end, this is the whole length. At the end, it will be close enough. This is co-current. Both are decreasing. For counter current, it is like this. You also know this goes like this, this goes like this. So it is heating this way, and this is cooling this way. And LMDT also same. LMDT is, so at, remember one thing, one people make mistake is, this is terminal 1, this is terminal 2. So delta T1 here, okay, and delta T2 here, not here. At 1 and 2 are these points, the starting and the end, not across, start and the end. So start and the end, this would be delta T1 minus delta T2 by ln delta T1 by delta T2. Okay, now let's wrap up things. Boundary layer, this is 4.64x by under root. So boundary layer thickness, hydrodynamic x. Okay, this is one formula for laminar. Okay, this I will cover in fluids perhaps. Grashof number. Okay, Grashof number is in GB. Okay, G beta delta T into L cube. Now 3 and 2. This is mu. Mu means kinematic viscosity. 3 by 2. So this is 1, 1, 2, 3. 1, 1, 2, 3. 1, 2, 3. I remember it this way. It's like a smile. Okay, so GB delta T L cube by mu cube. In case you forget the power, just remember 1, 2, 3. Okay, now for laminar, sometimes it is GR in case Grashof number, in case of Reynolds to find the Nusselt equation. In case of Reynolds, we put the Grashof number. Grashof is the buoyant force by viscous force, you know that. Okay, let's move to one most important thing, that is the NTU method. In here, the NTU, I will denote it by N. Okay, I will denote it by N to make it simple. Okay, NTU is UA by C min. UA by C min. C min means the minimum C of both fluids. Okay, let's say this is a double pipe heat exchanger. One fluid going here, one fluid going here. So the minimum, whichever it is, minimum C min is there. C here is, capital C here is M into C. Okay, MC delta T. So here MC is C min. So remember that. Here C is, like we write Q is equal to MCP delta T. So this C is, we are talking about the whole M into C. Okay, this keep in mind. Okay, I'm not writing MC here. So this is UA by C min. Okay, and for this we have another thing, that is C. C is C min by C max. Okay, max the other fluid, min that fluid, that is the minimum. So if you see, if we multiply this, C min will cancel out. So that way you remember it's in the denominator of N and it's the numerator of in C. So these are N and C. And now let me tell you the effectiveness. Effectiveness in case of co-current. Co-current, it is 1 minus exponential exp. Okay, exponential minus N. So minus co, because it is co, so minus. Okay, so 1 minus something would be there, into minus, and again this would be plus. Minus plus. Okay, this N is NTU as UA by C min. This C is C min by C max, and then 1 plus C. Whatever here it is, put here. This is co-current. Okay, minus plus, remember. In counter current, it is a little difficult, but not that difficult. 1 minus E, the same thing, minus N, just here minus minus minus. Okay, and here also, here write the same thing up and down in counter. This is counter current, same thing up and down. So write same thing up and down and just multiply C here. That's done. Okay, and if in case, let me tell you a special case in which if C is 0, when can C be 0? If C max is infinite. That means, let me tell you how C max, MCP, Q is MCP delta T in case of steam condensation. So in case of steam condensation, there is no delta T is 0. That means MC here, that we call C max, would be infinite, because Q upon 0, it will infinite. That means C is C min by C max. So this is C min by C max is infinite. So C is 0. Steam condensation, it is, remember that. Okay, now let's move on to one more thing, and that is we have done this. Okay, you note this, OCP, CC, cool, delta TC, cool is hot, that is UALMTD. Okay, this is a balance. And fouling factor, so fouling factor, okay, I'm not writing it like that, but fouling factor is just the resistance. It is the resistance. Let's say the factor is given F. Okay, then this is 1 upon F. This is the resistance. Okay, because fouling factor, this whole thing is the resistance actually that is given. Next, you can check the units of that factor that will be given in the question. Next, if I go to condensation, just remember two formulas. This H, the heat transfer coefficient bar. For the vertical, it is 0.943 for vertical. Okay, 943, just remember 0.94, let's say. And first write rho, then write rho GHK, rho GHK, and then mu L delta T saturation minus T wall. So this is T saturation minus T wall. Okay, rho GHK, and this rho here is rho L minus rho V, liquid minus vapor. Rho, remember this like this, rho GHK mu L by mu L delta T, or rho GHK by mu LT. Remember this way, else is a very big formula. Some people cannot remember it. This H is HFG fusion. Okay, not this capacity, this is heat of fusion, and this is 1 upon 4. Remember this, that H here is proportional to K to the power 1 upon 4 in the condensation. 1 upon 4 is important here. Same thing here would be there, rho GHK upon mu L T. T means delta T, delta rho 1 upon 4. Just write 0.725. This is for horizontal. Okay, this is also done. And here the average heat transfer coefficient is 4 by 3 H into local. Finally, radiation, last topic. Radiation, remember Q with shield. So Q with shield and Q the heat without shield. A very easy method is 1 upon n plus 1. How many number of shields are there? So Q with shield means if this is there and there is a shield over here that has some emissivity. So emissivity, let's say 1, 2, and this has some emissivity. So 1 upon n plus 1 would be there if the same emissivity is there. Q shield by Q without shield. This is one interesting to the point formula, and let me write the complete formula. Q upon A is sigma Stephen constant, delta T here by 4. So this is T4 minus T4 1 2 divided by 1 upon epsilon 1 by 1 plus epsilon 2 minus 1. Okay, cool. And because this is facing direct way, so I'm not writing FA, else FA will also come. This is the view factor. Let me talk about that. Okay, And one more thing is that rho plus alpha plus T, let's say some heat is coming here, it can either get absorbed or can get reflected. So reflected, absorbed, or can get transmitted. And total fraction, these are fractions, is 1. Because heat cannot just vanish away, it can either be absorbed, reflected, or transmitted through. One important thing to again see, this Stephen Boltzmann constant is 5.67, 567 10 raised to a minus 8. Okay, 5678. And there is also some like lambda Vane's displacement, Vane's displacement, lambda max is equal to, so lambda into T, lambda max into temperature is equal to 2.89 millimeter. Lambda T is 2.89 millimeter. And finally we have the view factor, or we can say form factor or something like this. View factor. Only remember two things here. One is F11 plus F12 if there are two bodies, or if say F13 plus F1. So F11, this means from 1 to 2. So F12 and 1 and 1 2, the total, if say there are two bodies like say 1 and 2, so this will total fraction. These are actually fractions, so this will be 1. Okay, because the total light or total heat coming from 1 to 2, 1 to 1 and 1 to 2, because only two bodies are present, so this will be 1. Okay, this is one way, one formula. The other formula is 1 to 2 with area of 1. So 1 1 is 2 to 1, 2 to 1 area of 2. Okay, these two are the important formulas. And lastly, let me write this also for a gray body. The epsilon doesn't depend, is not a function of temperature and lambda. Okay, epsilon is the emissivity. And also Kirchhoff's law, let me tell you, Kirchhoff's law means emissivity is, okay, I write it like this, emissivity is equal to alpha. Also for heat rate or heat flux, let's say, so it is emissivity from the transferred quantity and sigma T1 of the transferred quantity to the power 4 minus the receiving body, and this sigma will be there in this way. And the final thing, okay, the final thing, in case it comes, this is the energy, okay, that is C1, the energy. In case this comes, I don't think this will come in any paper, but this is kind of less. C1 is some constant, lambda to the minus 5. This is the energy of the radiation. So e to the power C2 is some constant by lambda T minus 1. I hope I'm just covering this because just by chance it comes. So these were all the things, and I hope you got everything here. I just tried to cover everything. So I hope you will like the video and share and subscribe, whatever you want to do. Just okay, and all the best.